Okay, so let's start. Any questions from the previous class? I'm sorry. Yes. The topic of RTL last week. Yeah. Any other questions? Okay, so in the last couple of classes, we were discussing the Chernoff bound and its consequences, right? So, in particular, we saw that the Chernoff bound gives us an exponential tail bound on the probability that a random variable deviates from its mean by a certain amount. Correct? So, for the case of Gaussian random variables, we were able to show the following inequality. By computing the moment generating function, we were able to show that the probability that x deviates from its mean by an amount delta is upper bounded by something that is exponential in delta square. Right? So in today's class, what we want to see is for what kind of random variables does such such tail bound hold. Right? In particular, for what classes of random variables does the right hand side equals e to the minus delta square times some constant. So our goal is to characterize this entire family of random variables, and as we'll see, not all random variables will satisfy such a bound. Right? So we'll study this class of random variables, what we call Subgaussian random variables. Right? So the main goal is to know when is what for what random variables x do we have this to be upper bounded by e to the minus maybe some constant times delta square. Any questions? Okay, so essentially the family of random variables that satisfy this bound are in some sense behave like Gaussians, right? Because what we want is the tail should decay at least as fast as e to the minus delta square, and that happens for a Gaussian. So the tail should decay at least as fast as a Gaussian, loosely speaking, and hence the name Subgaussian random variables. So a simple exercise, right? Sort of an extension of what you did in your homework one. You can show that you can compute all the moments of a Gaussian random variable. So for a Gaussian random variable x and any p greater than or equal to 1, you can show that this is equal to 2 raised to p by 2 times the gamma function p plus 1 by 2 whole divided by gamma half. So if, I mean, you can intuitively guess that if the following happens, then in some sense the moments of the random variable should behave approximately like a Gaussian. If the distribution has to be like a Gaussian, then the moment should also be roughly like a Gaussian. Right? And as a consequence of this, if you look at expectation of x to the p whole raised to 1 by p, this is going to behave roughly like some constant times square root of p for large p. So all of this is still for a Gaussian, and this is something that you can show just by using Stirling's approximation. Right. So let's now characterize the class of all random variables that satisfy this Gaussian-like tail property. So let's assume that x is some random variable. Random variable with I'm not going to assume anything else. I'm not going to assume anything about the mean or the variance or anything else at the outset. The following properties will all turn out to be equivalent to each other. Right, the first is exactly what I had earlier, with a minor twist. So the probability that mod x is greater than or equal to delta is upper bounded by some exponential. So it's e to the minus or 2e to the minus delta square divided by k1 square for all delta greater than 0. I'm sorry? This is for Subgaussian. So we'll say that any random variable that satisfies any or all of these properties is a Subgaussian random variable. Okay? So this is just a property. And I want you to note the following difference, that this is not absolute value of x minus mu. It's just mod x. The second is a statement about the moments. So expected value of mod x whole to the p whole raised to 1 by p. This is sometimes called the LP norm of the random variable x. Right? Essentially, you can prove that Now, what is x? A random variable x is just a function. So just as you define norms for vectors over finite dimensional vector spaces, you can also define norms for functions. And in particular, this is a function from what to what? Correct, event space to the set of reals, right? So over this space, you can define a norm, and this is one way of defining the norm. The LP norm, of course, I mean, if you think about it a little bit, it's not arbitrary. I mean, unlike this usual norm that you define over Euclidean spaces, the LP norm depends on the distribution because it has this expectation function. Okay? I'm sorry. So K1 is some constant. Okay. This is less than or equal to K2 times square root of P for all P greater than or equal to 1, where K2 is some other constant. Okay. One thing to note is that K1 and K2, these only depend on the distribution, nothing else. Immediately, it is not obvious how K1 and K2 are related to each other, but I'll tell you what it is at the very end. Okay. For now, K1, K2, and the other constants that I'll introduce, all of these only depend on the distribution and nothing else. What's the third property? Third property is something about the moment generating function of x square. So expectation of e to the t square x square is less than or equal to e to the k3 t square for all t less than or equal to one over k3. I'm just making statements right now. Okay? So I'm saying that all of these properties are equivalent to each other. So if some random variable satisfies one of these properties, then it should satisfy all of the other properties. The fourth looks somewhat similar to the third property, but it seems somewhat weaker. So expectation of e to the x square divided by k4 square is less than or equal to 2 for some constant k4. Okay, so all of these four properties are equivalent to each other, but in addition, if we have expected value of x equal to 0, so if it's a zero mean random variable, then this is equivalent to all of the other four. So it is expected value of basically the moment generating function is less than or equal to e to the k5 square t square. This is less than or equal to 2. Which one? There is some k5 So there is some k1 which satisfies this, some constant k1 which depends only on the distribution. It depends on the distribution, but this k1 is independent of delta. Similarly, here k2 depends on the distribution but is independent of p. Right? Same here, it depends only on the distribution, not dependent on p, and so on. All right. Yes. So if a random variable satisfies 1, then it satisfies 2 and vice versa. The same thing holds for any pair of properties. And for the properties 1 to 5, you take k, so ki and kj in any of these properties is some constant, some universal constant. Okay, the universal constant doesn't depend on the distribution. Yeah. I can upper bound, that's why I say it's upper bounded by a constant. Yeah. Let me say Cij for some universal constants. Yes. Let me make it more. Okay. I'm sorry, can you speak up? The ratio is, yeah, it's going to be the same for all distributions. That is, if I have two different distributions which satisfy property 1. For the first distribution, I could have some constant here. For the second distribution, the constant would be different. But the ratio of these for property 1 and property 2, that's going to be the same for all distributions. And you'll see that as soon as I give the proof. You see that will never happen. So one thing you have to keep in mind is that these are all upper bounds, right? So the same constant could potentially hold for two different distributions just by taking the larger one of the two. Right? So these are not equalities, these are inequalities. So you can have the same constant for two different distributions. All right. So yeah, so it will become clearer once you see how you get one property from the other. Which one? Not necessary. You'll see that the ratios you can still take them to be, they may not be the best universal constants, right? So let's assume that the constant is 10 in this case, okay? For some distribution, k1 turns out to be 10. Maybe that's the tightest constant, maybe it's not, right? Even if I substitute k2 to be equal to 20, which is larger than k1, it will still satisfy this inequality, right? So let's assume that let's say that I take k1, let's say k1 equal to 10 satisfies this. Okay, and k2 equal to, say, maybe 5. I'm just making up a number. Okay, then what is this ratio? It's 2. Right? Even if I take k1 equal to 20 and k2 equal to 10, these inequalities still hold. These are valid. Does that make sense? K2 equal to 6 will also work for this inequality. Yes. Okay. So what I'm trying to say is that you can choose this to be some universal constant. Okay. Yeah. So let me go through the proof and maybe that makes more sense. Essentially, I'm hiding K1, K2, K3 and so on. So I can say that if this holds, I can fix a particular K, let's say K1, then K2 will be, I don't know, maybe 10 K1. So I could state all of these properties in terms of a single constant K, but that's not particularly relevant. So if I know one of these Ki's, then I can choose the rest of the Kj's to be some universal constant times that particular K. Right? Does that make sense? Okay, so let's assume that the first property holds. I'll first try to show that if the first property holds, then the second property is also has to be true. If a random variable satisfies this for all delta greater than 0, then it should also satisfy this for all p greater than or equal to 1. I'll first try to do that. Correct. So I'll show that if 1 is satisfied, then 2 is satisfied. If 2 is satisfied, then 3 is satisfied, and so on. In the end, if 4 is satisfied, I'll show that 1 is satisfied. So it will be circular, which means that all of them are going to be equivalent. Okay, so right now what do I want to do? I want to bound expected value of mod x whole to the power p. So let me start with that. Okay, given that this holds, any guesses as to how you can derive or get a bound on expected value of mod x to the power p? Okay, as a hint, you need to use something from your first homework. So in your homework, you saw a different formula for expected value of random variable. No, I'm not asking you to use Markov's inequality. It's just an expression for a different way of evaluating the expectation. Not MGF. So for a non-negative random variable x, there was an expression for expectation of x, right? Yeah, it's sort of using a tail probability, but exact. It was there in the homework, right? Correct. Correct. So it's equal to, so if y is a non-negative random variable, then expected value of y is equal to integral from 0 to infinity probability that y is greater than or equal to, let's say, v. It's not equal to this directly. You essentially can get something by splitting the positive and negative parts. Correct. Okay. Yeah. So let's try to just use this. What do you get? This is integral from 0 to infinity. The probability that mod x to the power p is greater than or equal to, say, let me call it v for now, dv. Okay. I have to be careful because this is mod x to the power p, whereas I have bound on mod x. Correct. So what do? This is also equal to integral from 0 to infinity probability that mod x is greater than or equal to, okay, so let me use a different expression. So let's suppose that I want to write it in this particular form. Right? What is the change of variable that I need to make? Sorry? Fine, all of this is for p greater than or equal to 1. I'm fixing p before. If p is, sorry, can you repeat? Correct. Sure, yes. So I'm saying that in the statement, I've already assumed that p is greater than or equal to. So I'm fixing a p greater than or equal to 1 before. Okay, yeah. p into p minus 1, right? Okay, that's very good. Now let's just apply this inequality. This is less than or equal to integral from 0 to infinity e to the minus u square by k1 square pu raised to p minus 1 du, right? What next? Yes. So up to this step is fine. I've done nothing but just apply this expression for expected value of y and a change of variable, nothing else. Right? Now what's next? What do I need to show? I need to show that this is less than or equal to k2 times square root of p. So let me do another change of variable. Yeah, fine, I can take u square equal to something. Let me take u square by k1 square equal to something. So let's do another change of variable. Let's set u square by k1 square to be equal to w. By 2. Sorry, why do I need to? Okay. That integral is a constant. But the integral is a constant that depends on p. So two things. One is, I mean, this depends on p. I need to find the exact dependence on the right hand side on p. I need to show that this essentially behaves like root p whole raised to p. I want to show that this is square root of p whole raised to the p. And I also, not just that, this is some k2, and I want to show that k2 is at most some constant times k1. I also want to know that dependence between k1 and k2.
Because you can change this according to this.
I'm sorry, can you? Here. Okay, here. Correct. Yes.
That is we can reframe.
Reframe in terms of what?
It's instead of
Okay. That's not going to be enough. I mean, that will be almost trivial. because I want this particular thing, because this is exactly how it behaves for a Gaussian, right? So I know that this is what the moments behave like for a Gaussian. So I'm saying that if a random variable is sub-Gaussian, then there are these different ways of characterizing it. Okay? So in certain applications, I will not be able to show that the random variable satisfies this directly, but maybe I have some handle on the moments. So if I am able to show that the moments satisfy this, then I know that it is sub-Gaussian. Or if I'm not, or if the only thing I am able to show is this property, then I know that it is sub-Gaussian, and I get all of the other properties for free. Right? That's why I want each of these properties separately. I want to characterize the distributions or class of distributions based on these 4 or 5 properties. Okay, so this is going to be less than or equal to, or this point is just equal to integral 0 to infinity e to the minus w square times p times, I think it's going to be w whole raised to p minus 1 a1 by 2. Yes, p minus 2 is it? So there's a 2u du e to the minus, right? So this is e to the minus w. So let's see. So u to the p minus 2 times u du. This is what I have, right? This is equal to a1 root w whole raised to p minus 2 times a1 square by 2 dw. So this is equal to p times a1 to the power p times integral from 0 to infinity. Let me take the 2 outside as well. e to the minus w times w raised to p by 2 minus 1 pw. Right? That's exactly gamma of p by 2. Right? So from Stirling's approximation, I can show that gamma p by 2, I mean even otherwise, is less than or equal to p by 2 whole raised to p by 2. Sorry? P by 2 whole raised to p by 2. I mean, because what is the gamma function equal to? Or what is the relationship for gamma x in terms of gamma x minus 1? Yeah, so gamma n is n minus 1 gamma n minus 1, right? So gamma p by 2 is p by 2 minus 1 times gamma of p by 2 minus 1, which is equal to p by 2 minus 1 into p by 2 minus 2 times so on. So you easily get p by 2, this is upper bounded by p by 2 whole raised to p by 2. Yeah, it's okay, I'll just take p by 2. I'm happy with this. So this is less than or equal to p by 2 k1 raised to p times p by 2 whole raised to p by 2, which is k1 raised to p times p by 2 whole raised to p by 2 plus 1. Or this is equal to so k1 by square root of 2 whole raised to p times square root of p whole raised to the p times, I think I still have another p by 2. So expected value whole raised to 1 by p, this is less than or equal to k1 by square root of 2 times p by 2 whole raised to 1 by p times square root of p. Which part? Which one? Ah, okay. That's correct. So there should be another 2 over here. So there should be a 2. These 2's cancel out. So this is just P. Right? Thanks. Okay, what can I say about P raised to 1 by P? Can I bound it from above by a universal constant for any P greater than or equal to 1? So can I bound P raised to 1 by P above by a universal constant? What does P raised to 1 by P look like? Okay, let's just take a look. Let's vary x from 1 to 100 in steps of 2. So this increases up to a certain amount, and then it just goes to 0 as P tends to infinity. So in any case, this is at most 2, right? I just use a loose upper bound. Right? So this is less than or equal to, say, square root of 2 k1 root P. So this is, I call this k2. So we now know that k2 is at most square root of 2 times k1. I can choose a k2 which is root 2 k1, and the bound will still go. Right? Any questions? Why it is? Just from, you can prove it more formally, right? But no matter how I increase P, for P between 1 and infinity is bounded by 1.4 something. So P raised to 1 by P is at most 1.4 something, and it's therefore it's at most 2. It's some universal constant. And in particular, I can choose it to be 2. So K2 is at most root 2 K1. Any questions? Sure.
That is going to just change the universe.
It's just going to choose a universal constant. The smaller the universal constant, the tighter the bound that I get, right? And in general, yeah, I all I need to know is that we're not going to really care too much about what the best universal constant is, but as long as we have some hold on that, that's enough. Because it, in many of these problems, we'll be interested in regimes where some parameter, for example, the number of random variables in question, is going to be very large. So we're interested in large n anyway, so these universal constants won't really matter.
That inequality can be defined.
Which one?
Right. K2 is less than or equal to
K2 is okay. So what I want to say is that this quantity is less than or equal to K2 times square root of P for some K2, right? And what I'm trying to say is that I can choose K2. Okay, so I can, so anything, so let's think of K2 as the best possible constant. All right, let's assume that, so I know that expected value of mod x whole to the power p raised to 1 by p is less than or equal to K2 times square root of p. And suppose that K2 is the best possible constant which satisfies this. What I know is that for sure this best K2 is at most square root of 2 times K1, right? Because the square root of 2 was obtained by taking sort of a loose bound on p raised to 1 by p anyway. Okay, so the exact statement is this is less than or equal to K2 times square root of p for, or let me make it even more precise. So suppose 1 holds, then there exists some K2 which is at most square root 2 K1 such that this holds. Okay. There's some K2 and I only have an upper bound on this particular K2. I can choose it to be square root 2 K times K1. I could choose it to be something larger than square root 2 times K1. This inequality would still hold. But I don't have to choose it too much larger than square root 2 times K1 to get a bound. Any questions? Okay, so now let's assume that that 2 holds. Okay, what do we want to show? We want to show that expected value of t square x square, e to the t square x square is upper bounded by some e to the k3 times t square. Any guesses? we know that this holds. Exactly. So first try is you just expand this, use Taylor series for e to the power x. So it's going to be t square x square whole to the power L divided by L factorial. Right? Very good. So this is equal to summation L equal to 0 to infinity t to the power 2L by L factorial times expected value of x to the power 2L, which is the same as expected value of mod x to the power 2L because 2L is even. Okay. What next? Let's just use this form that we have. L factorial times k2 times square root of L whole to the power n. Both these have to be true. This is L equal to 0 to infinity k2 square t square whole to the power L divided by L factorial times two L whole to the power N. Right? Now, what do I want to show? I somehow want to make sure that this, I want to show that this is less than or equal to summation L equal to 0 to infinity k2 square t square by the L factorial. If I could show this, then I'd be done. But I can't really do that because I have this 2L whole to the power L sitting. So it's not exactly true. Right? Because this would be e raised to k2 square t square. Alright. So we'll aim for something a little less. We'll first try to bound the denominator. For that, again, we'll use Stirling's approximation. So L factorial is actually greater than or equal to L by E whole raised to the F. So this quantity is less than or equal to k2 square t square whole divided by L by E whole raised to the L to L raised to the L to E k2 square t square whole to the power. Question? So I've used this inequality for L factorial, and yeah, this L to the power L and this L to the power L cancel. So what I end up with is 2e whole to the power L times k2 square t square. Sorry, the whole thing is not. There is a power L. K2 square t square whole to the power. Right? Okay. What is this the Taylor series expansion of? What is summation L equal to 0 to infinity x to the power L? Um, you can't, right? It will be a lower bound, so I can't really do that. Yeah? Yes. So what is that equal to? It is equal to 1 by 1 minus two e k2 square t square for correct, exactly. So what condition should that follow? So this whole quantity should be less than or should be less than 1. Less than or equal to 1, or mod t less than or equal to 1 over root 2e k2 square. Right? Okay. Yes. Can you speak up a bit? Has to be. That's right. Right. Okay, we're almost done. Do we know a bound on 1 minus x in terms of e to the power x? One minus x is what do I want? I want an upper bound on this particular quantity, right? Which means that I want a lower bound on the denominator. So I want 1 minus x greater than or equal to something. this will turn out to be greater than or equal to e to the power minus 2x, but not for all x. Right? This will only hold true for x less than half. Zero less than or equal to x less than or equal to. For e k2 square t square, this holds true only when mod t is less than or equal to less than or equal to. Okay, so this is what the right hand side is just e raised to k3 square t square, and I can choose k3 to be essentially, or k3 square to be equal to 4e k2 square. Less than or equal to I'm sorry, can you speak up? 1 minus x is lower bounded by e to the power minus 2x. So 1 by 1 minus x is less than or equal to e to the power 2x. Any questions? I mean, ultimately, we're just sort of playing tricks here, right? We're just using bounds on the only sort of tools that we're using are bounds on e to the power x and Stirling's approximation, and just manipulating either the moment generating function in terms of moments or moments in terms of tail probabilities and so on. We're just going back and forth between these. Yes. In which one? Um, yeah, I gave the 5 things. Let me see. Correct. This should have been K3 square. Thanks for correct. Okay. Now, if 3 is satisfied, can you claim that 4 is also satisfied? You just have to choose T. Yeah. So suppose that 3 is satisfied. Can I choose a T such that this becomes 2? What should I choose? Equal to? So let's do some calculations. And what I want is e raised to k3 square t square to be equal to 2, or k3 square t square should be equal to log 2, or t square to be equal to log 2 times, or log 2 divided by k3 square. So t equal to root questions. Now let's assume that 4 holds. Yes. Which one? Correct. Okay. How would you choose the? No, forget about that. What value of t would give the right hand side equal to 1? Oh. What is log 1? Doesn't matter what base it is. Log 1 to base anything is what? Log 1 to any base 0, right? So I have to choose t equal to 0, which Oh, but I need expected value of e to the, sorry, this should have been x square. Write it more carefully. What I want is expected value of x square divided by some k4 square, where k4 is a positive constant. In this case, it's just k3 square by log 2. If no finite value of k3 would give me this equal to 1, the right hand side equal to 1. So it has to be greater than 1. You can choose it to be any other constant. I could choose it to be 1.5, I could choose it to be 1.1, doesn't matter. So in that sense, 2 is kind of arbitrary. Which one? Again, not so much. But that's not so important. It has to be greater than 1. That's the only restriction. Any other questions? Which one? Correct. 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 No, again, right? So if I choose a larger value of the constant here, the left hand side becomes smaller. So definitely any larger constant is definitely going to satisfy this particular inequality, which means that I can choose a k4. There exists some k4 which is less than or equal to k3 divided by square root of log 2, which satisfies this. That's the statement, right? It's not that any k4 less than or equal to k3 divided by square root log 2 satisfies this. There is one, and that is enough. Okay, so again, to prove 1 from 4, I'll have to rely on some bounds on the exponential. So you can show that e to the power x can be upper bounded by x plus e to the power x square for all x. Yes.
Yes, shown the equality for 2, right? X square by k, 1 square is equal to 2.
For 2, yes.
Something specific. Sorry.
Yeah, I could choose 1.5, I could choose 1.2, it doesn't matter. Yeah, it's so that 2 is not particularly important. It should be greater than 1. So in that sense, case 2 is kind of arbitrary. I just want to show that this is upper bounded by some universal constant. So assuming that this is true for all x in R, expected value of e to the power tx is less than or equal to expected value of tx plus expected value of e to the t square x square. right? I want to show that 5 holds. So what is the assumption in part 5? What is the expected value of Tx? 0, because I'm assuming it's a zero mean random variable. But we already have a bound on expected value of e to the t square x square. I've shown that 1 through 4 are all equivalent to each other, so I can use any one of them. So what is a bound that we've shown? This is upper bounded by e to the power t square times k3 square, but for t less than or equal to 1 over k3. So this holds only for mod t less than or equal to 1 over k3. Right. Now what if again we'll just use a different bound, nothing else to. So I claim that 2tx is, okay, let me pose it to you. What is the relationship between 2tx and x square plus t square? It's less than or equal to this, and why? You just, so if I move this to the right hand side, then I just get x minus t the whole square, which has to be greater than or equal to 0. So t times x is less than or equal to x square by 2 plus t square by 2. We'll also assume that mod t is greater than or equal to 1 over k3. We'll see why. So expected value of e to the power tx is therefore less than or equal to expected value of e to the power x square by 2 plus t square by 2, which is less than or equal to expected value of x square by 2 times e to the power t square by 2. This quantity is at most 1, and I'm assuming that t square is greater than or equal to 1 over k3 square. So this is less than or equal to this is t square over 2, so this is definitely less than or equal to for some k. I only need to worry about mod t greater than or equal to 1 over k. Did I use what?
The bound.
This one? No, I didn't use here. Oh, sorry. This one. Yes. Okay, sorry. Let's assume that 1 through 4 holds. Because I've shown that 1 through 4 are all equivalent. That's right. Correct. So maybe I'll do that in the next class because we are out of time. But you're right. So what I first need to show is that 1 holds from 4. And then assuming that 1 through 4 holds, then the first part also holds. So So effectively, that you'll see that it ends up being to show that 1 holds from 4. You just have to make use of Chebyshev's inequality. That's all effectively that you do. Which one?
For A, for B, what is greater than 1 by 3.
Correct. Correct.
And less than equal condition from the previous one.
Which one?
Like important be less than equal to 1, right? Like e power x, explanation of e power x squared, right?
Correct.
Yeah.
So expectation of e to the power x square by 2. Yeah. So So this is at most. Sorry, it's as x. So this is expected value of e to the power x square by 2. I'm loosely speaking, I'm using property 3, I guess. Right? Sorry, property 4.
So that will become 2, right? When we are choosing ln, we will choose ln e instead.
We should choose. It doesn't really matter. Okay, so I can just show that this is at most some universal constant c.
ln what?
Correct. I can't choose that to be equal to ln1. But in any case, this is going to be bounded by some universal constant times this. So I'm already over time, so maybe I'll stop here.